Welcome to Microscope, a series of in-depth, critical, comprehensive, and informative conversations about issues that really matter in community. No scripts, no written questions, minimal or no editing. This is what journalism does best. Join me, Steve Betchkel, as we sit down and get down to the matter at hand. First thing I want to ask you is, what is your field of study? What's your background in science?
Well, I have 2 degrees in geography, a bachelor's and master's from the University of Wisconsin, and then a PhD in, it was in the Wildland Resource Science program. Really, it was the Forestry and Resource Management program at the University of California, Berkeley, with an emphasis on forest ecology, landscape ecology, and conservation biology.
Would it be simplifying it to say that you know a lot about fire and trees?
I know a lot about landscapes and forests and ecosystems in general, and what I study a lot the last 20 or so years is the effect of different kinds of disturbances on ecosystems, but especially forests. I love forests a lot. So, but I've studied everything from soil erosion and changes in runoff and erosion processes and flooding to high severity fire, what comes back after fire, how have landscapes changed over decades to centuries or longer, and the effects of climate variability, wet periods, dry periods, and now what seems to be directional climate change on the health and well-being of forests. In particular, I've spent my adult life living and working in the mountains of northern New Mexico, studying and monitoring the health of forests. And when I first came, it was a wet period in the early 80s that lasted till the mid-90s. And then in 96, it turned to dry, and our forests started to not do very well, and they started to die and they started to burn, which forced me to learn a lot more about it. And it turns out this wasn't something just restricted to northern New Mexico. This is something that was starting to show up elsewhere in the West and even globally with drought and warmer droughts that we're seeing these days.
Okay, can you pin a year on that? When would this have been that you noticed these kinds of changes? You said it went from wet to dry when?
It was the winter of 95, 96. So it was nearly snowless in the mountains of northern New Mexico that winter.
Were the words climate change popping up, global warming popping up in 95, 96?
Sure. No, I mean, ever since I've been a student, a grad student, a university student, starting in the late 70s, early 80s, it was a topic. But the amount of knowledge about climate change, directional climate change, has grown a lot, and the evidence for it has increased a lot over this time period. So, the emphasis on it has increased through time, over the course of my career. But I was aware of it as a student, 35 years ago.
Okay, all right, that far back.
Oh yeah,
yeah, people
sure.
were talking about it then.
Oh yeah, probably 40 years ago, really.
Weren't they talking about the coming ice age and shifts in that too at that time?
Well,
was there an argument?
We don't want to go there. No.
All right, okay.
Yeah, no. That argument was the nuclear winter argument was if you detonated, if we blew up a bunch of nukes, it would be like volcanic eruptions, but worse.
Well, let's go this way. Ecosystems are always changing. They're in shift. They're in.
Yep. And indeed, I started both my master's and PhD were studying landscape change, ecosystem change in this one particular mountain range in northern New Mexico, the Jemez Mountains, for some hundreds, thousands of years using multiple lines of evidence. And so yes, change. Yes, nature is not static. Nature is dynamic. It's always changing.
But when it comes to trees, in your scientific experience, you've noticed that heat and drought have an effect on trees. What does heat do to trees that you see that is perhaps shaping the future of forests?
Well, the issue from forests and actually almost all ecosystems on Earth these days is that while there's always been variability and there's always been change, that variability for extended periods of time is constrained within a range. So there's this historic range of variability. And so things are kind of like, oscillating, but the weather's not static, the climate's not static, but it's been within a bounded range for a long time.
There are hot seasons, there are drought seasons, there are wet
Sure.
seasons in forests, yeah.
Yeah. But what's different these days is that there's a trend that there's an awful lot of evidence showing that it's driven by anthropogenic forcing of the composition of the atmosphere, fossil fuel emissions largely, but other things as well. And but there's a directional trend on the temperature of the planet. And it's pushing the values, particularly of extreme temperature events, starting to push outside the range of the frequency and magnitude of that historic range of variability. So individual plants and species are increasingly not as well adapted in the places that used to work for them as they used to be.
So they can't shift their morphology, their physiology to catch up with heat?
So for the last 20 years, the effect of drought and warming temperatures on forest growth, on forest health, and patterns of tree death, tree mortality, has been something that with many colleagues, first in the southwest US and then westwide, and for the last 15 years globally, been working with trying to elevate, put more attention on trying to understand what does it take to kill a tree. It turns out we know how to grow trees in models pretty well, but we can't realistically kill them in a model. We can't simulate, because tree mortality is a very, well, it's a complex process, and it doesn't happen quickly. There's a lot of different factors, they're interacting, and trees have many compensatory processes. They can adapt morphologically in terms of their growth. They can, for example, in a given year, they can invest more in leaves and height growth. If conditions are favorable, like it's wet, then you want to grow tall and put lots of leaves in a big canopy because you're competing for light and space with your neighbors who are also growing fast in that year. But if it's a dry year, all of that extra biomass above ground you have to support and keep alive. And if you can't photosynthesize very much because it's too dry, then you might invest more in roots. And so over a period of time of, trees, if climate shifts gradually, trees can change their morphology to some degree. Their physiology is adaptable to some degree, but it's bounded. There's limits, which is why different species live in different places, right? It's why banana trees don't grow in Wisconsin, for example, because unless they're in a greenhouse, because it just is too cold, among other things. But there is a range of conditions which any given tree species can grow in normally, and there's even genetic variability within the species, and so this is why trees don't live to be hundreds or even thousands of years old in some cases without being quite adaptable to the historic range of variability for that site. But it turns out that if you start pushing outside that historic variability, the dominant plants, the dominant trees that were in that place were tuned to that historic range of variability, and now the climate variability, the climate envelope is starting to move enough that during extreme drought or extreme heat events, we're seeing unusual tree mortality pulses in every ecosystem, every forest type, every major forest type around the planet.
In Europe, in Australia, in Africa,
every continent except Antarctica, where there are no trees, but every forested continent, but not just every continent, every major forest type, from tropical wet forests to mangroves, mangrove forests. In the last year, there's been mortality events down in Australia in mangrove forests that are being attributed to drought and heat stress. And mangroves, trees that live in the water. But from tropical wet forests to savannas in Africa or South America to temperate forests in eastern North America or Central Europe to boreal forests, in Canada and Asia, of course, Siberia, and temperate forests in the West. Western North America has had a lot of tree mortality associated with drought over the last 20 plus years, and the warming temperatures, where the warming signal is starting to be strong.
So what you're saying is, though, that worldwide, this phenomena was triggered about the same time worldwide through forest communities, and B, it has to do with the increasing temperatures and dry conditions.
one of the challenges of studying tree mortality at a global scale is we don't have good baseline information globally. And even in particular regions or localities, particular landscapes, the quality and the time length, time duration of the historic information is quite variable.
Okay.
But so we don't actually, what we know when 2010, so 6-7 years ago, with 20 colleagues around planet Earth, we put together the first global overview of published literature since the 70s on drought and heat-induced tree mortality. And what you can see in the scientific literature, there's a huge increase in the amount of literature being published, but that could just be an artifact of people paying more attention to it, which is part of what some of us have been trying to do. We think it's an important and a worrisome issue that needs more attention. In a few landscapes, what we can say is within the historic time period of the last 100, 150 years or so, when people have records, written records, places like Australia, places like Western North America, places like in Europe, actually, where they have longer records than that, we're seeing tree mortality pulses that are anomalous relative to that historic period of record, that are unusual. But there's so many places on the planet that there aren't good records. But what we can see, in any case, is that whether you're in the Amazon or Australia or Alberta, that combination of severe drought and warmer temperatures is leading to significant and in many cases historically 100+ year anomalous tree mortality events.
So what I'm getting at, I guess, is these aren't coincidental. These are happening for a reason because of conditions worldwide.
Well, there are other places on the planet where trees are growing better than we've ever measured them.
Really?
So these are places where the tree mortality is happening are the places where we have gotten severe drought. But drought's a natural phenomenon. It happens, right? Climate is variable, precip is variable. No matter where you are, even in the wettest places on Earth, there are time periods it's drier, which locally is a drought. So almost everywhere on the Earth has been warming. There's a few places that, because of the circulation patterns of the atmosphere and the oceans, that there hasn't been much warming, or even a little. In some cases, like the southeastern U.S. has not warmed much in the last 20 years compared to rest of North America. Okay, some places like the Arctic are strongly warming. They're warming more rapidly than the mean value around Earth. There's many global changes going on. Climate is not the only thing that's changing on the planet Earth. Okay, and it's not just CO2, it's many other gases in the atmosphere that have various effects. Some of them have warming effects. Some things actually have cooling effects, like the particulate that come out of smokestacks. And so this is part of why there's debate about all the different effects of all the different human forces. Changing land use cover changes the amount of sun's energy that's absorbed versus reflected, and these things all feed back through the Earth's system. But one of the things CO2 does, increasing CO2, that is sort of the core gas that plants use for photosynthesis. Currently, there's not a global system for monitoring the trends, the status and trends of the health of the world's forest, including how well they're growing, including how much stress they're under.
Not even regionally? You mean worldwide?
Globally.
Okay.
Yeah, no, there are regions like the Forest Service has a variety of different ways they try to look at forest resources in the U.S. But those don't go back very far. Combinations of plots on the ground, and you go back and do repeated measurements, flying with airplanes in every state and mapping where insect and disease outbreaks are going on. And again, that goes back 25 years, like to the 80s. Maybe 30 years now, and where you have data that you could consistently apply. Satellites, you can look at things globally by satellites, but you're not seeing individual trees in these satellite images.
Right.
You're seeing aggregates of trees, and there's a lot of things going on inside a single pixel, say, of a Landsat, which is our best data set that goes back about 40 years now. And but since the 80s, the size of a pixel is 30 meters on the side, right? So like a third of a length of a football field on the side is one little pixel on a satellite image, and there's a lot of things going on inside that pixel.
Yeah.
A tree could die, but everything underneath it could green up.
Right.
All the shrubs and grasses could green up, and that pixel could look healthier in some ways than if the tree, greener than if the tree was dominating it. So you can't, so anyway, the point is that so forests are not responding uniformly across Earth, neither in time nor in space. So when I first came to New Mexico, I started, since the summer of 1982, I started doing field work. So this will be, whatever, the 36th year in a row I've been doing field work in the mountains of northern New Mexico, since I did my master's and PhD in the 80s there. And that was a wet period. In tree growth, when you look at the tree ring records, I work with dendroecologists, tree ring ecologists a lot, and so we can reconstruct tree growth for more than 2,000 years in northern New Mexico and reconstruct episodes of drought stress and heat stress now, and fire histories, and so there's a lot of things we can do with it. And what you see when you look at the last 1,000 years or 2,000 years of tree growth, that period from the late 70s to the early 1990s was one of, if not the best periods of tree growth in the whole 2,000-year tree ring record. And at the time when I was there, people were remarking, wow, trees are growing great. It was a great place to be, a tree. The southwest US, Arizona and New Mexico, in that period of the 1980s into the early 90s. Starting with the very dry winter of 95, 96, which was regional drought. The jet stream stayed north, the storm tracks didn't get down as far south as Arizona and New Mexico. We got almost no snow. And immediately, that spring and summer, we started popping big fires, and there started to be more tree stress. Tree growth declined markedly. And we've basically been in drought ever since. And the drought intensified. There were pulses. Different years have been different. And meanwhile, during that same period, the last 20 years, it's been warming significantly. And warming increases the water stress on trees. So both precipitation and temperature have big effects on trees' abilities to grow and the amount of stress and can kill them. If you don't have enough water, or if it gets too hot, or in some cases if it gets too cold. But what we're seeing globally is things are getting warmer, and when this really matters is during drought periods. Okay? And so when trees are under water stress, obviously if there's not precipitation, if it doesn't rain enough, or if there isn't snow and the snow melts and goes into the soil, trees are going to have problems if there's less than they need. And so if it's unusually dry, trees are stressed. It's totally different depending on, in the Amazon, the ability to tolerate it is 2 months. If you're a juniper in Arizona, it's years.
Okay.
Right? You could shut the thing down without any precip, but in 3 months, trees in the Amazon are starting to keel over. All right? It's seasonally dry in the Amazon. There's a dry season, even in the wet parts of the Amazon. But if it gets more than about 2 months, then there's effects. But even then, it takes a couple years to kill things normally. But some things die quicker. Every species is different. The systems are different. Anyway, I need to get back to your main question, which you want to excerpt, is the role of temperature. What is the role of temperature on increasing drought stress and killing trees? Well, trees get their water primarily from the soil. And the way they get water from the soil to their buds and leaves at the top of the tree's surface, which could be 100 feet or more above the ground, is basically there's little conduits through the wood tissue that extend from pores in the leaves, called stomata, through the xylem vessels in most trees. The wood goes down to the tiniest little rootlets. And they're connected in little chains. And so when a water molecule evaporates off of the leaf surface from one of those stomata, it pulls the next water molecule in a chain. It's like a siphon. If you're like siphoning gas out of a car, it's like that. And you can imagine, if you only got to siphon it up 2 feet, that's one thing. But imagine if you got to siphon it 100 feet up, if you're at the top of a tree and you got this long hose and you're... So the taller a tree is, the more tension it takes to pull the water. And meanwhile, the soil particles there's surface tension, and they're trying to hold on to the water unless the soils are really wet. But during dry periods, when the soils are wet, there's no problem. And then water goes up easily. But when the soils start to dry out, then the tension that it takes for this transpiration, which is when a water molecule evaporates off and it pulls, the tension, called plant water potential, starts to increase inside. And at some point, these little chains of water going up these little vessels can break. They can pop open and they basically get an air bubble in them. It's called cavitation, okay, and embolism in the, and there's thousands of these around the circumference of a tree where the water is going up, and some of those can cavitate, and it's not a big deal, and it happens routinely in trees. People are studying, trying to understand how many of these can pop before they can't repair enough of them. But basically, if you start popping more than about a third of them, many trees are in trouble, and if you pop, if more than half of them cavitate, trees are likely to die, or at least significant portions of their canopy is likely to die back. Trees don't like that to happen because they spent years growing that canopy, and they need it to compete with their neighbors. They don't want to get shaded out. So, to avoid desiccating their water vessels and having the water columns cavitate, they can close the stomata on their leaf and needle surfaces. There's kind of a little fail-safe mechanism that does that. So when they're under water stress, they can close the stomata and stop losing water. And they do that routinely on hot summer afternoons all over the world. And then they'll open up during the night and be ready to go the next morning, and it's all good. Sure. But if you're under protracted drought stress for weeks, months, and you got to keep those stomata closed because there's just no water coming and the soils have dried out, those same stomatas where the water transpires out is where CO2 goes in for photosynthesis. Right. That's the gas exchange, both water vapor going out and CO2 coming in. The plant splits off with sun's energy, the carbon, holds on to the carbon, makes cellulose, right. And oxygen goes back out. Well, the plant can't photosynthesize when it's got those little pores, those stomata closed.
It's like the plant is holding its breath, huh?
So, and what it's doing is actually starting to, if it goes on for a long time, the plant starts to starve. They store carbohydrates, the things they make through photosynthesis, in their tissues all over the place within the plant's tissues. So they store a lot of stuff, just like we do. Mm-hmm. And they can access it when they're under water stress. They have to draw on their energy reserves. Mm-hmm. But when it goes on for weeks, months, or years with long-term droughts, the trees weaken, and then they start to be attacked by insects and diseases because their defense mechanisms involve the energy that they need and things like resin, like pitch in a pine tree. That's actually very expensive to produce from a biochemical standpoint. And when a tree is weakened and can't photosynthesize, it just can't produce enough resin to defend itself. Mm-hmm. And so things like bark beetles can bore in, the tree can't bury it and smother it in this pitch, which is full of little poisonous compounds that are also expensive to produce. And so the bark beetles start to get the upper hand, their populations grow, and they can kill huge areas. But it's the water stress that's doing this. Now, the question is, drought can do that. And historically, droughts kill trees. This is not a new phenomenon on planet Earth. We see this. There's historic records. Droughts kill trees. Tree physiologists, we all know this. If you don't water the plant in your house, it's going to die eventually, right? Plants need water. All life needs water. But warming temperatures increase the atmospheric demand for moisture. If you warm up the air in this room, the parcel of air in this room, nothing else, the only thing you change is you warm the air up. At equilibrium, the air can hold more water. Thus, it essentially wants to hold more water. So what that's doing is when the air is warmer, it increases the pull by the atmosphere on both plants to pull water off their leaf surfaces and from the soils, which is where the plants get their water. So it's kind of a double whammy in terms of amplifying the water stress on the plant. It doesn't matter very much when it's wet. when the soils are wet and the air is wet, if the air is a bit warmer, okay, the plant is still able to get water up to it, into itself. But when it's dry, during drought conditions, those warmer temperatures are amplifying the drought stress on the plant, makes the drought last longer, it makes the drought more extreme. And this seems to be one of the factors that's involved in increasing the amount of tree mortality that's going on in droughts. And we saw this in the southwest US, and we've published on it with colleagues, I have, comparing the last severe drought before the drought we're probably still in the southwest US was during the 1950s. And I had actually reconstructed some of the effects of that drought when I was doing my dissertation research on landscape change in this mountain range, the Jemez Mountains in northern New Mexico. And I was on the ground, you could see all these dead ponderosa pine tree logs in the early 1980s when I'm walking around, and I asked people, well, what's that about? Oh, there was a windstorm in the 1960s, people said. Well, maybe there was, but the trees were already dead. Turns out they died in the mid-1950s because of a severe drought, and you can see it in the air photos. I found written documentation of it, and we could date the wood, and we can date the tree rings, and we put all that story together, and you could actually map the tree mortality between 1954 and 1958, in the 50s, because there were air photos from 1954 and 1958. Trees were alive in 54, they're dead in 58. The 50s drought was a very severe drought. Went from about 42 to 56. The worst year of it was the last year, 56, in terms of a precip standpoint. But then we were in this window, and so in the late 80s with a colleague, a good colleague friend of mine, David Brashears, who's was at Los Alamos National Laboratory at the time. He's now at the University of Arizona. But we wrote a paper, kind of a classic paper, I suppose, a small paper, about the effects of how it caused the bottom edge of the ponderosa pine zone to die back as much as 2 kilometers in less than 5 years in the middle of the 1950s.
Okay, the southern limit, you're talking about latitudinally?
No, the elevational limit. So these trees, right, there's more than a mile elevational gradient on these mountains.
Okay.
And it's drier at the low elevations of these mountains, and it's colder and wetter, and a shorter growing season, higher. And something like ponderosa pine on the slopes of the Jemez lives in the upper 2/3 of that zone. Well, the bottom fringe of that zone died back in the 1950s. And it did not come back after the 50s. Even in this wet period, the forest did not recolonize into that area where it had died back in the 50s drought, even though there were a few surviving tree seed sources, mother trees survived. One could wonder about the role of temperature in that, but we won't go there. I think the trees had pushed downslope during the Little Ice Age, which ended in the mid. So during kind of the late medieval period and ending in circa 1850, so the ponderosa pine pushed down slope during that cooler, wetter period. They could extend farther down slope. And then even during the 20th century, we weren't in that cool period. It had already kind of bumped up a notch from the Little Ice Age, at least in the northern hemisphere. And then it's been warming since. So anyway, we had some idea, but we kind of predicted. We didn't kind of predict. We said the next time there's a severe drought in northern New Mexico, this is in 1990, late 90s, excuse me. I might have said late 80s before. But in the late 90s, 1998, we published this paper based on my dissertation research. And we said, the next time there's severe drought in the region, we could expect a lot of trees to die and probably more high severity fire. Well, it turns out at the time that paper was published, we were at the beginnings of this ratcheting up severe drought episode that started the winter of 95, 96 and intensified. By 2000 it was quite severe, and by 2002 was an extraordinarily dry but also warm growing season in New Mexico and Arizona, and several million acres of trees died in 2002 to 2004 in the Four Corners area. The part of the world where I am in the southwest. So a couple species of pines, Douglas fir, but also shrubs and grasses. Just the water stress on these plants was extraordinary. And it turns out when you use tree rings, and in a paper led by a colleague that was published in 2013, a guy named Park Williams, kind of a rising star, he developed something called a forest drought stress index from tree rings of tree growth. And basically Park's big advance was, we always knew trees grew a thinner tree ring during a dry year.
Sure.
And that was used to reconstruct precipitation going back for, in some cases thousands of years. Park found a temperature signal for Arizona and New Mexico in the tree growth that had not been picked up before. And it was young guy, huge data set. He could look at a big data set with new ways, and he was able to see that growing season daily maximum temperatures, when they are warmer during the growing season, trees grow more poorly in the Southwest. They're using mostly winter precipitation that falls in the winter, goes into the soil, and then they're growing in the spring and early summer. But when it's warm, and so when there's more winter precip, trees grow better. No news there. That was been known for 100 years, quantitatively. But he found a temperature signal. And he put the two together, and when you put the two together, the temperature during the growing season and the precip signal, and you put those together, he had a predictor that was the R squared in a correlation coefficient was 0.84, which is ridiculously high. I mean, it's surprisingly high. It was the strongest climate predictor of tree growth that anybody has developed. And it was at a regional scale. And then the temperature was half the strength of that. And that was a new finding. Well, when you look with this forest drought stress index, and so you look back for 1,000 years of tree ring record, and look at the variability, and there have been bad droughts and bad periods, and there's an oscillation that you see there that's probably driven by some sloshings of the Pacific Ocean, in particular, that change where the jet stream goes when it comes over North America and affects the winter precip. But the drought we were in at the time that this study is going on, which was in the early 2010s, I mean, we're in 2011, 12, 13 was another brutal, dry, warm window. But it turns out 2002 was the worst year for tree growth in Arizona and New Mexico in the last 1,000 years.
Wow.
But just in the tree ring growth. I mean, you can see it in the growth. And by his index, it's not that it was drier than every other dry year in the last 1,000 years, but it was the combination of warmer as well as drier. And so this drought, the drought we're in right now is now achieved, at least by this forest drought stress index measure with tree rings, is at least as severe, and probably more severe now, than the worst drought in the last 1,000 years, which was previously thought to be the late 1500s based on tree rings. But that's how poorly our forests are doing now. So if you came in the 1980s, you would say, what a great place to be a tree. It was an awesome, I mean, trees were growing well, the forests were getting thick and dense. Well, for the last 20 years, that's all gone into reverse. Trees have been stressed, they put on fewer needles, they grow more poorly, they've been dying, they have many different kinds of health problems, and there have been a lot of high severity fires. And so basically the forest probably overshot density-wise a bit during the wet period, and they're getting squeezed back by this drought. We think, again, at some level, colleagues, we've published a paper earlier this year, we think this kind of process is natural to some extent, that trees naturally do this because there's often this decadal scale oscillation in climate driven by these ocean sloshings. And during wet periods, the vegetation tends to get a little bit thicker. But if you're in kind of a marginally dry part of the world, like savannas in northeast Australia, or maybe forests in the mountains of the southwest US, that there's a tendency to get thicker during those wet periods when trees have a lot of moisture, they can grow well, and they're competing with each other then for space in that period. But then when you go into this, 15 to 20 year dry spell, that has to get squeezed back. And so there's just not enough water to sustain that much biomass. So either insects start to kill trees, they grow more poorly, and there's often more fire in these systems. Warming temperatures amplifies probably both the up and the down, because the warming during the wet period, the atmosphere is holding more water vapor now. And this is why you hear, like extreme events, you hear this discussion, the storm intensities are greater than they used to be. Well, it's because there's actually literally more water being held in the atmosphere, so when you get the conditions for a storm, there's more water potentially to come out that can be triggered. But it's also true that it's amplifying, it seems, the kinds of conditions that make deep, extensive droughts. So this is part of why it's complicated to talk about what's going on globally
Sure.
with trees, because there's places in our short record of the last just 30 years where we actually can see with satellites and have the best knowledge. Some places have been wet in that 30-year episode, and forests are growing better than anybody's ever measured them before. That was kind of the situation in the Southwest in the 1980s. But what you see is that can change.
Mm-hmm.
And now in the Southwest, there's been so much stress and so much mortality from drought stress, insects, and fire in the last 20 years. There's great concern that these forests are being replaced by shrub fields in a lot of places.
Mm-hmm. Yeah, they won't bounce back from the stress.
Perhaps not, in part because the amount of tree mortality during this dip, during this extreme dry, hot event, is killing more of the parent trees. But also in part because, and so you're getting big holes in the forest where there's not much, there's few mother trees to reproduce, even when the wet period comes. The trees are waiting for the next wet period, the mother trees. But when the next wet period comes, it'll still be warmer. It may not be as favorable. We'll see. We haven't got there yet. Mm-hmm. In the Southwest U.S. But anyway, this is happening all over the planet. It's, you're getting different combinations through time. But what we see is that for something that lives a long time like a tree, if you project only during the good period, you say, oh, well, look at these trees. What are you worried about? Trees are growing awesome here in Central Europe. And they are, for the most part, at the moment. The warming temperature is actually beneficial if water isn't limiting in many places, because the growing season's longer, the tree can grow longer, and there's more CO2 in the atmosphere, so they're able to take up the CO2 easily, even during periods when there's a little bit of drought stress. Yeah. But when you have severe drought stress and the trees have to stay shut down, then the warmer temperatures are hurting.
Is part of this formula that it's less predictable, that we maybe had ideas, scientists had an idea that this is how it worked in the desert Southwest, or this is how it worked in the American Southeast, or this is how it worked in Australia. Are those models kind of shaky now? Have they been shifted so that you can't predict as well how a forest in a certain part of the world is going to do because it's more variable, it's more fragile?
Yes, in a sense that although I would say that what the model said before is if it stays within this historic range of variability, we would expect to get back the same dominant vegetation if you have a fire.
Yes.
It just might take 100 years for it to go through successionally, but we would expect to get ponderosa pine back if that's what was there before, or white oak and red maple somewhere here in Wisconsin. But one of the challenges is that every species responds individualistically. So it isn't to changes in the environment, to changes in climate, to changes in environmental drivers of whatever sort. So we're used to a certain community of plants and animals, and we think those come as a package. And 100 years ago, ecologists talked about them like they were a package that went together, this community type. Right, the sugar maple, beech,
hemlock
type, okay, and that this type was bound together. Well, other ecologists, literally for 100 years ago, were debating that, and for the last 60 years, it's actually very clear when you study other kinds of long records that the communities we see today are not what was there thousands of years ago.
Okay.
That individual plant and animal species have changed their distribution slowly through time, and they mix and sort in various kinds of ways.
They've changed their dance partners over time, perhaps.
Yeah. And so you can't model a whole community type, but to model individual tree species, we also can't model. People try to do this with models. And basically what they do is they look at the correlation between the distribution of sugar maple and what is the climate space in North America that sugar maple grows in. So you look at that and you say, okay, if it gets warmer than this, it doesn't do well. And if it gets colder than this, it doesn't do well. And if it's drier than this, it doesn't do well. And if it's too wet, it doesn't do well. So you kind of put these boundaries on the climate space where you would expect sugar maple to grow, based on where it is today and what the climate historically was. But the climate is shifting. And people use these kind of models to predict where individual species will go. But of course, the individual species are not operating in a vacuum. They're also competing with other species. They're also dealing with human changes to the system, other things, acid precipitation, excess nitrogen in the system, invasive insect species. Emerald ash borer is in the process of taking out a whole genus, all the different species of ash in eastern North America as we speak. So there's all these other kind of things that make that hard. That's kind of a correlational model. There's other people that have tried to model physiologically. Well, let's get into the guts of how photosynthesis happens and water relationships within a plant, and let's measure a plant. Let's do experiments and test how much water and heat stress it can take and see how the plant responds. Those experiments are showing plants have some plasticity, some adaptive plasticity, and are trying to determine how much there is. But it turns out we've been doing this with 2 species in New Mexico for the last 20 years where this problem emerged, right? Almost 20 years ago. And so there was interest in it early to do experiments there. So colleagues of mine have been doing this, and I work with them a bit. And what we see is these 2 species. One's a little pine, pinon, with edible nuts, Pinus edulis, and one is a small juniper tree, Juniperus monosperma. Those 2 tree species are probably as well characterized physiologically as any 2 species on the whole planet in terms of drought and heat stress experiments. And there's been 3 sort of major experimental sites where they've been stressed that are, like 150 miles apart in one case and another 40 from a different site. And these trees don't even behave at the 3 different sites quite exactly the same, the model. So it's challenging and messy if you want to really get into the bolts of it, nuts and bolts of it. But we can grow the trees in the model relatively realistically. But we still have a hard time determining how much stress a tree can take before it actually dies. There's too many different processes involved in tree mortality.
Yeah. And that would be in a vacuum anyways, is what you're saying.
Yes, and that's the other problem with it, exactly. And so at this point, if the climate models are right about the trajectory of where climate on this planet is going, and they seem to be, they're working pretty well from what I can read. I'm not a climate scientist myself, but when you run the models backward, they get you basically, they get you the kind of historic patterns we see, and the last number of decades, the projections and the models are lining up pretty close. And so if those models about where climate's headed this century are accurate, what we can see is that it's a big change from the historic. The warming alone is enough to change probably what tree species can be dominant in a lot of places, but we can't tell you, well, 1 degree more or ½ degree more, or well, it depends on how severe the drought is. But what we can see is that already on this planet, that under conditions that are historically a severe drought, but not unprecedented from a precipitation standpoint, severe droughts happen, but you make it a little bit warmer, and there's a lot of trees dying in these sites. And so we can see that trees are already, their natural distributions are tuned pretty close. They have some flexibility, some adaptability, some compensatory capacities, but we don't know whether it's enough to tolerate the amount of warming that we see even in the coming decades. And in New Mexico, for example, Arizona and New Mexico, on these 2 species, pinon and juniper, using 8 different ways of trying to model how these 2 species will respond to warming this century, using a couple different kinds of climate models. By mid-century, they're going to die. if the models are right, based on what we can tell, the majority of the conifer trees in New Mexico are going to be, during basically whenever the next drought cycle comes, are probably going to get taken out, it looks like. And it doesn't mean they're all going to die everywhere. There's parts of the landscape that's wetter, there's little pockets, the soils are deeper, it's on north-facing slopes, it catches runoff from the slopes. So there's going to be spots that'll be much more resilient, and these trees will last for a long time. But over large parts of their current distribution, it looks like things are going to they're not going to be able to continue to live during extreme drought events. And so, this is making people in parts of the West kind of nervous about the fate of forests. But right now, our models in general are not good enough. There's challenges with every one of those models. Every one of those models has issues, but they're different issues, but they all give a pretty convergent answer, which gives you some sense that we're talking in the right kind of zone, perhaps, at least based on our best knowledge now. But globally, there are no models that I believe currently about the future of vegetation on this planet, because we can't model the mortality processes accurately, realistically at this point. And so I'm helping people try to do that a little bit from an ecology standpoint, because the modelers are usually not ecologists.
What about the forests in Wisconsin? Is there a chance that the forests in Wisconsin could shift, change, get sick, disappear? We'd lose some of our forests up here. I mean, I know you're saying that a lot of these models can't tell you factually what's happening, but from what you can see, from what scientists do know, is it possible that that's happening in not only the U.S. here in California and Wisconsin and British Columbia, where pine bark beetles are eating trees up, but in Australia and Africa and South America? Is it happening in those same kind of ways in other places in the world, that we're seeing these die-offs, historical drought-related die-offs that might not be able to replenish themselves in times of wetter conditions?
Yes. No, I mean, that is what we're seeing. We're seeing, all forest types on this planet. There's huge concern, for example, over the Amazon basin. I mean, there's concerns over land use. Obviously, if people cut it down and turn them into soybean fields, that's one thing. But there's a feedback in a place like the Amazon. Half the precipitation is cycled within the system. So it's water that's transpired from the trees and then condenses in the clouds and falls again. And if you don't have trees doing all that recycling, if you turn it into cattle pastures, there would be less precip.
Yeah, the system kind of breaks.
The system breaks, yeah. So there are these, and these are one of the big concerns, is that all these changes are actually, we think of things sort of changing in a linear trajectory, but actually so many things are, there's compensatory processes that living organisms try to hold things within a bounded range so that they can live. Mm-hmm. But when it's like the frog in the boiling pot, right? It can live for a while, and it's starting to cook, but if you increase it slowly, it doesn't even know. But at some point, the proteins start to coagulate, and the frog just dies. Mm-hmm. And this is what it is. So you get these thresholds, these non-linearities in these ecosystems, and that's the way these drought events happen. In terms of mortality, tree mortality is, trees can tolerate a lot of stress for a long time, often. Although if it's an extreme stress, sometimes they can go down fast from water stress. It depends on the species. But at some point, there are thresholds in these systems. There's limits, and we don't know where they are, because historically, trees weren't being forced against those limits, because they were growing in places where they weren't exposed to such an extreme drought-heat combination. But those combinations are changing as the climate changes, and so these experiments are happening all over the planet. And we, in a sense, that forests are being subjected to combinations of drought and heat that these forest types haven't seen for hundreds, thousands, could be a really long time. Anyway, not over the lifespans of any of the trees that are there. And so we're seeing unusual mortality events already starting to emerge. Enough to tell us that probably we don't know exactly what it is, but if you throw another degree warming into the mix, that a lot of stuff is going to die. Not everything, probably. Depends. The more diverse your forests are, we can see that. There was a cool study done in West Africa, in Ghana, And somebody had some data from 30 years ago about these forest plots. And then there was a big drought that lasted a kind of a chronic drought for a decade. And a PhD student, a woman named Lucy Fawcett from the UK, went back and found these plots and re-looked at what the forest types were. And they still had about the same biomass and about the same density of species, but the species had turned over to drier species types. But these are tropical forests where there's a lot of species possibilities, right? You or I might not have even noticed. That would be kind of the lucky case, where the drought was chronic but not extreme enough in any given year to cause the system to kind of crash. And so if climate changes slowly, that's what we would expect. But what we notice, the events we do notice, the ones that I've helped compile and work with people on, are the ones that are the extreme events. This year, like 2002, which then extended, actually it was from 2000 to 2004, it was very dry, but with 2002 being this extreme year in the southwest US, and you get this millions of acres of trees dying, multiple species all across the landscape. That gets your attention. Right now it's California. It's the forests in particularly the southern portions of California, the southern half of the state or so, where they've had multi-year drought and it's been warm and it's finally pushed trees past their threshold point, and the insect populations, bark beetles in particular, their populations have built up and they're taking out, something on the order of 20% of the trees in California are in the process of dying.
Yeah, that could shift a lot of things.
Yeah.
20% of the trees going. Yeah.
Yeah.
So trees, you said trees are adaptive. Why can't trees just seek out these pockets, find the favorable pockets? At one time we were under sea. We were under seas. One time we were, it was a different habitat. Things change. The plants move and they change. And why can't that just happen again?
If it's long enough time periods, it will happen if they don't go extinct. It's the speed at which the change is happening today. For something like a tree that has a long generation time, right, things that live centuries like trees, they can't move that quickly. And so we have studies from like when the last ice age ended, right? Wisconsin, where we're sitting right here in Eau Claire, Wisconsin, was under a mile of ice 18,000 years ago. As that ice melted and retreated and plant life came back to the landscape, from pollen you can reconstruct how fast trees moved north to recolonize, the northern part of North America that had been under ice. And it seems they can't move that fast. And so that's the main answer. It's just that trees that happen to be growing in those nice pockets will probably hang on and do fine for some time in these places, in the little favorable microsites. And there's people who are trying, from a conservation standpoint, are now trying to identify those places on the landscape that are likely to be most resilient to drought and heat stress. And thinking that we should make sure we're trying to protect those kinds of places, and thinking about perhaps helping move populations of various plants. If the time comes that you can see their populations start to crash in the landscape as a whole, those would be the best refugia for them. We see that there's refugia on landscapes, in general, but this is a conservation kind of a frontier right now, is thinking about where those places are on landscape, but they're going to differ for different species, because different species need different things.
Okay, so it seems obvious to me that we're not just talking about plants here. Animals are very dependent upon vegetative habitat, birds, for example. So if the system breaks, if the habitat, we're talking about plant communities that are fine-tuned to certain organisms, from bugs to mammals, that's got to put some stress into the animal kingdom as well. And I would think it will put stress into the human resource category too, because if we don't have forests, if the land dries up and blows away like a dust bowl, aren't we talking about possible repercussions to how we live?
Yeah, well, forests are really important on this planet. They provide environmental services for humans of many sorts. Economic value of wood products, They protect watersheds. That's one of the core reasons we have so much national forest in the West, is to protect the watersheds up in the mountains. All the people are living down in the valleys, and farmers who irrigate, and cities that need the water, and all of that goes down there. If the forests, burn or die, certainly it changes things. Obviously, for plants, for animals, vegetation is the habitat, core element to it. That's what they eat most, it's the base of the food webs. That's all true. And at a global scale, forests provide this huge environmental service relative to fossil fuel emissions, and in terms of buffering or reducing the effect of increasing CO2 concentrations. About a quarter of the excess CO2 that humans emit through fossil fuels into the atmosphere, about a quarter of it is every year pulled out. A quarter of the excess put in that year, about a quarter of that doesn't stay in the atmosphere. It's pulled out by photosynthesis, by vegetation, mostly forests on the terrestrial land surface. Oceans pull another quarter or so out, just mostly by diffusion as the CO2 concentration in the atmosphere goes up, it kind of pushes a little bit more CO2 to dissolve into the ocean, where CO2 plus H2O makes HCO3, carbonic acid. This is why the oceans are getting more acidic, that you may have heard and read about. And
problems with corals,
corals,
things like
other things with shells, right? Exactly. It gets a little bit harder to make these calcium carbonate things they protect themselves with as it becomes more acidic. Because again, they evolved within a certain range of acidity of seawater to function. A lot of people trying to figure out where the breaking point is for that, for different organisms. But anyway, if forests, instead of being this sink, that's kind of a sponge, providing this free service of taking a quarter of the excess stuff we're emitting and pulling it back and sequestering it, at least temporarily, in vegetation and in the soils through the roots. What happens if these forests start to die in large, big old trees? And it turns out big old trees disproportionately sequester more of the carbon. One giant tree holds more carbon than many small trees because of the volume to surface ratio of these big dominant trees. And so when big old trees die, that's a lot of carbon that is going to go back, that goes back to the atmosphere. It's one of many reasons why old trees, ancient trees, in addition to being, just spectacular organisms and having special ecosystems associated with them in many places, but they're also important even just from a carbon budget standpoint, because they sequester way more carbon in their wood than lots of small trees. So old growth forests are important to try to maintain. But warming seems, both theoretically and empirically, meaning there's the physics of water movement in a tree. Theoretically, it's harder to get water to the top of a tall tree. It kind of seems logical, you're pulling it farther from gravity, but when you do the physics of it, it seems to be true. And empirically, we see that during these drought mortality events, big trees are disproportionately affected in terms of both growth and mortality. So
that seems odd to me. Why wouldn't the little trees be more fragile than the big trees?
Sometimes really small trees are, because they're just not rooted deep enough to get down in. But we think it's largely because of this thing that if once you're established as a tree, at least sapling sized, trees make a big effort in roots right away to get down to the zone. But then, if you're a 10-foot high sapling versus a 150-foot high, dominant tree, during that drought event, that dominant tree just can't get that water up.
Yeah, it's losing canopy and leaf structure and all that stuff. Yeah.
Stuff that it invested in over many decades. And that tree is providing shading to the small tree. The canopy tree is taking the full heat stress of the sun, the whole temperature stress on the canopy, on the leaf surfaces. And if you're measuring actually right on a leaf surface, it gets really hot in the afternoon. And so those trees are actually providing a service to the smaller trees in a sense of, when you go into a forest, it's cooler, right? If you're out and walking in a field and you're getting cooked in the sun and all of a sudden you go into the forest, it is. The microenvironment is cooler. So anyway, it's a concern. Some of us, think ancient old trees are just intrinsically marvelous. The redwoods, the giant sequoias, the bristlecone pines, and trees like that elsewhere all around the planet. But they're also important. Ecologically, they're important socially, they're important economically, and they mean things to people. Right. Humans value big old trees. We have stories about old trees. There's religions that revere old trees. We have the tree that some treaty is signed under or whatever. And there's a sense of loss when big old trees die. And I think in part because they live so much longer than we do. At least big old ones do. And so there's this sense of timelessness about them. And having lived in a place where for the last 20 years there's been a lot of big old trees dying, there's a palpable sense of loss societally when these trees die, much less whole hillsides of forest die, that as well as all these kind of measurable effects, economically, and how it does for water and what it does for wildlife habitat and carbon sequestration. But there's a spiritual and an aesthetic and just an emotional connection that we have that is involved as well. So,
Well, we've talked for about an hour. I think that's a good place to end it. So thank you very much for talking with me about this topic, Craig.
yeah, my pleasure, Steve.
Thank you for joining us today for Microscope. We've got more on many great topics. Look for us online at www.cvctv.org.